Evaluating the uplink performance of a low Earth orbit (LEO) communication constellation over Africa. This study focuses on the impact of rainfall attenuation on satellite communications. LEO satellites are increasingly seen as a solution to provide affordable broadband internet in unplanned and sparsely populated areas, particularly in Africa, characterized by tropical and equatorial climates with heavy rainfall patterns. Current International Telecommunication Union (ITU) models for characterizing rainfall attenuation are based on data from temperate regions and may not accurately represent conditions in Africa. To address this, the study applies the ITU-R P.618-8 model with data from ITU-R P.837-7, Tropical Rain Measuring Mission (TRMM), and Global Precipitation Mission (GPM) satellite to determine the level of attenuation and available link margin for a LEO system such as Telesat. The specific and predicted attenuation for 6 candidate ground stations, Abuja, Hartbeesthoek, Cairo, Longonot, Port Louis, and Praia, is computed, with results presented for 0.001% 1% unavailability time in a year. By setting a link margin of 0.36 decibels, the available link margin and the best candidate ground station for a LEO system such as Telesat is determined. This research aims to provide insights into the feasibility of LEO satellites in bridging the broadband gap in Africa, considering the significant impact of rainfall on satellite communications in these regions. The approach used in this study can be implemented for other potential ground stations and LEO communication systems over Africa. Accurate quantification of rainfall attenuation is crucial for reliable communication services in tropical regions. This study focuses on Telesat, a low Earth orbit (LEO) satellite constellation, and its performance across 6 candidate ground stations in Africa. The ITU-R P.618-8 model is utilized, incorporating rainfall rate measurements from NASA's Global Precipitation Measurement (GPM) satellites. Previous research has shown that the ITU-R model overestimates rainfall attenuation in tropical regions. To address this, the study objectives are to compute rainfall attenuation using the ITU-R model with rain rate data from GPM for the 6 candidate ground stations, and to establish the uplink performance and availability for each station. The system parameters for Telesat are outlined, including frequency, bandwidth, transmit antenna diameter, EIRP, elevation angle, free space path loss, receiver antenna gain, system temperature, link margin, and altitude. 6 candidate ground stations are selected based on global coverage, accessibility, and infrastructure availability, with their geographical coordinates determined using Google Earth. The ITU-R P.618-8 model is employed to calculate rainfall attenuation, incorporating rain rate measurements from GPM satellites. The results are used to calculate the carrier-to-noise ratio, CNR, and link availability for each ground station, establishing the quality of service, COS, of Telesat in the proposed ground stations. The best candidate gateway station for Telesat is determined based on the results. This study contributes to the existing body of knowledge by providing a more accurate method for quantifying rainfall attenuation for LEO satellites over tropical regions. The findings will be useful for designing and optimizing LEO satellite communication systems, such as Telesat, to ensure reliable and efficient communication services in tropical regions. The selection of ground stations for Telesat uplink performance analysis in Africa is based on 3 key criteria: geographical location in the middle of the oceans, a minimum distance of 2,000 kilometers between any 2 stations to ensure uncorrelated weather conditions, and realistic or potential locations characterized by space activities. 6 candidate ground stations are selected, listed in Table 2, and shown in Figure 1, which displays their distribution on a world globe. Integrated multi-satellite retrievals for TRMM and GPM-IMERG rain intensity data for the 6 candidate ground stations are obtained from NASA's website, covering the periods from January 1, 2005, to January 1, 2014, for TRMM, and January 2015 to June 2020 for GPM. The IMERG dataset combines passive microwave sensors hosted in low Earth orbit (LEO) satellites with additional data from geo-infrared (IR) satellite estimates and ground precipitation gauge analyses to improve accuracy. Notably, GPM data is more accurate than its predecessor, TRMM, due to improvements such as increased inclination, addition of 2 radar frequencies, and the inclusion of 165.5 GHz and 183.3 GHz channels for solid and light precipitation sensing. The estimation of predicted rain attenuation is based on the ITU-R P.618-8 model, a 10-step process. The fourth step requires rainfall intensity rate exceeded for 0.01% of an average year data to calculate specific attenuation using the equation upsilon-R, decibel per kilometer, equals kappa R 0.01 alpha, where kappa and alpha are coefficients that are a function of Telesat's uplink 28.5 GHz frequency, obtained from ITU-R P.837 by integration. Assuming vertical polarization, which limits attenuation by raindrops, the predicted attenuation above 0.01% for the year is calculated using the equation A 0.01 equals upsilon RLE, dB. Table 2 lists the selected candidate ground stations in Africa, including their location, latitude, longitude, and height above sea level, while Figure 1 displays their distribution on a world globe, labeled GS1 to GS6, according to the order in Table 2, designed using Standard Toolkit, STK. The calculation of rainfall attenuation rates for different percentages of time exceeded is discussed in this section, utilizing the ITU-R P.618-8 documentation. The predicted attenuation rate is calculated using equation 3, which considers factors such as the percentage probability under investigation, the magnitude z, and the ground station's latitude and elevation angle. This calculation aims to establish the effect of rain on the CNR, available link, and the best performing ground station. The CNR is calculated by taking into account the EIRP, G/T ratio, free space path loss, other losses including rainfall and atmospheric absorption, and the thermal noise floor. This computation utilizes the Freeze transmission equation, equation 4, a time series analysis of area average precipitation rates from January 2005 to January 2014 for 6 proposed candidate stations: Port Louis, Praia, Cairo, Abuja, Longonot, and Hartbeesthoek, is also presented. Figure 2 illustrates this data, providing insights into the variability of precipitation rates across these locations over a decade. This information is crucial for understanding the impact of environmental factors on satellite communications and can inform strategies for optimizing system design and performance. A comprehensive analysis of the satellite-based precipitation estimation system is presented, focusing on the link budget calculation. The received power at the satellite, denoted as PR, is derived as a function of the effective isotropic radiated power of the ground station antenna, EIRP, receiver gain, GR, system temperature, T, free spacepath loss, FSPL, sum of all other losses, OT loss, Boltzmann constant, K, bandwidth, B, and rain attenuation, ROT. This expression is crucial in determining the signal strength and quality at the satellite. The derived expression is PR equals EIRPGR, 4 pi, FSPL plus OT loss, KB, 1 plus ROT, T. This formulation takes into account various losses and attenuations, providing a comprehensive understanding of the system's performance. Figure 3 displays the contour map of the time-averaged overlay of merged satellite gauge precipitation data, obtained from the 3IME-R GMV06 dataset, at a spatial resolution of 0.1 degrees and monthly temporal resolution, from January 2015 to June 2020. This figure provides a visual representation of the precipitation patterns over the study area, which is essential in evaluating the performance of the satellite-based precipitation estimation system. The contour map highlights the 6 candidate stations, which are critical in the system's design and implementation. The link budget calculation is a critical component in the design of satellite-based systems, as it determines the signal strength and quality at the satellite. The inclusion of Figure 3 provides a visual representation of the precipitation patterns, which is essential in evaluating the system's accuracy and reliability. This comprehensive analysis is essential in understanding the system's performance and limitations, which is critical in the design and implementation of satellite-based precipitation estimation systems. This section of the research paper presents the results of the study on the impact of rainfall on satellite communication links in Africa. The analysis is conducted using three different data sources: ITU-R P.837-7, TRMM, and GPM. First, the authors compute the rain intensity for each candidate station using ITU-R P.837-7, which serves as a baseline for comparison. They then analyze TRMM data to retrieve rain rates for the same stations, and the results are plotted in Figure 1. The findings indicate that Hartbeesthoek, Longonot, and Abuja experience high rainfall intensity, while Cairo, Port Louis, and Praia have lower rainfall intensity levels. Next, the authors use GPM data to cover the period between January 2015 and June 2020. The time-averaged rain rate overlay maps for each station are generated using NASA's online software, Giovanni. These results conform to the previous findings from TRMM, with Hartbeesthoek, Longonot, and Abuja experiencing high rain intensity, and Cairo, Port Louis, and Praia showing lower levels of rainfall. The ITU-R P.837-7, TRMM, and GPM results are then used in subsequent calculations. Using the rain intensity values from ITU-R P.837-7, the average rain rate, specific rainfall attenuation, and CNR are computed for 0.01% unavailability time. The CNR results are presented in Table 3. Similarly, the average rain rate, specific rainfall attenuation, and CNR are calculated using TRMM and GPM data, with the results shown in Table 4. The findings indicate that Hartbeesthoek and Longonot stations have the highest altitudes and record the highest rainfall attenuation rates. Although the correlation between altitude and rainfall attenuation is not explored in this study, literature suggests a relationship between latitude and rainfall attenuation. The lowest attenuation levels are recorded at Port Louis, Praia, and Cairo, leading to lower CNR values. However, none of the stations could achieve their link closure for the 0.01% unavailability time. The ITU-R P.837-7 model significantly overestimates rain attenuation values for candidate ground stations, particularly those with low rain rates. Results in Table 5 show the highest overestimation percentages for Cairo, Praia, and Port Louis, with corresponding low rain rates depicted in overlay contour maps. This suggests poor model performance in regions with low rain intensity. A comparison with updated GPM data from 20,152,020 reveals a similar trend of overestimation, with overestimation percentages of 105%, 142%, and 97% for Praia, Cairo, and Port Louis, respectively, as shown in Table 6. In contrast, regions with high rain rates, such as Hartbeesthoek, Longonot, and Abuja, exhibit lower overestimation percentages of 54%, 59%, and 70%, respectively. Figure 5 provides a graphical comparison of rainfall attenuation rates for candidate stations based on rain rate values from the ITU model, TRMM, and GPM satellite data. The results illustrate significant overestimation of rainfall attenuation by the ITU-R P.837-7 model, particularly in regions with low rain intensity. These findings suggest that the ITU-R P.837-7 model may not accurately capture rainfall attenuation characteristics in regions with varying rain intensities. The results highlight the importance of using updated and accurate rain rate data, such as GPM, to improve the accuracy of rainfall attenuation models. The comparison of the ITU-R P.837-7 model with GPM data reveals a consistent trend of overestimation, indicating that the model may require adjustments to better capture rainfall attenuation characteristics in different regions. A comparative analysis of rainfall attenuation data from the Tropical Rainfall Measuring Mission, TRMM, and the Global Precipitation Measurement, GPM, satellite missions was conducted for 6 candidate ground stations. The objective was to determine which mission's data provides more accurate results for calculating link margins in satellite communications. A comparison of TRMM and GPM estimation percentages in Table 5 revealed inconsistent correlations across the stations, likely due to differences in the time periods covered by the datasets, TRMM 20,052,014, GPM 20,152,020, and improvements in GPM measurements. Given these discrepancies, the authors opted to utilize GPM results for further computations. Carrier-to-noise ratio, CNR, values were calculated for different unavailability times, 1%, 0.5%, 0.1%, 0.01%, and 0.001%, using GPM data, with an uplink center frequency of 28.5 GHz. The results, presented in Table 6, indicate that only the Hartbeesthoek and Longonot links do not close under the given conditions. A detailed breakdown of rainfall attenuation, CNR, and available margin for each station is provided in Table 7. The results highlight the significant impact of rainfall on satellite communications, with Cairo experiencing the highest attenuation at 61.4714 decibels and Abuja having the lowest at 24.1363 decibels. The available margin for each station was calculated, demonstrating the additional power that can be added before the link becomes unavailable. These findings emphasize the importance of accurate rainfall data in satellite communications, particularly when calculating link margins. By comparing and utilizing GPM data, the authors provide insights into the reliability and efficiency of satellite communications under varying weather conditions. This study examines the response of 6 candidate ground stations to rainfall attenuation at C-band, 48 GHz, and Ka-band, 26.540 GHz, frequencies, focusing on unavailability times of 1%, 0.5%, 0.1%, 0.01%, and 0.001%. Rainfall data from the Global Precipitation Measurement (GPM) mission is used to calculate the cumulative distribution function (CDF) of rainfall rates, which are then applied to the ITU-R P.837 model to estimate rainfall attenuation. The results for Ka-band uplink frequency, 28.5 GHz, show that Cairo and Port Louis have the highest available link margins, with values above 30 decibels for all unavailability times. Longonot and Hartbeesthoek stations exhibit lower margins, ranging from 2,025 decibels. Abuja and Praia have the lowest margins, below 15 decibels for most unavailability times. In the case of C-band uplink frequency, 6 GHz, the available link margins are generally higher due to lower rainfall attenuation at this frequency. All stations exhibit margins above 35 decibels for all unavailability times, with Cairo and Port Louis showing the highest margins. The study highlights the importance of considering rainfall attenuation in the design and operation of satellite communication systems, particularly in regions with high rainfall rates. It also emphasizes the need for accurate rainfall data and reliable models to estimate attenuation accurately. Future work could involve refining the models used and incorporating other environmental factors that affect satellite communications. A study assessing the impact of rainfall on satellite communications in Africa has identified optimal gateway stations for a low Earth orbit (LEO) communication system, such as Telesat. The analysis leveraged rainfall data from the Tropical Rainfall Measuring Mission (TRMM) and Global Precipitation Measurement (GPM) missions to calculate the link margin and carrier-to-noise ratio (CNR) for 6 candidate stations. The results indicate that Cairo, Praia, and Port Louis surpass the link margin at 0.01% unavailability time, rendering them suitable gateway stations for LEO communication systems over Africa. Abuja also surpasses the link margin, albeit at a higher 0.5% unavailability time. Conversely, Longonot and Hartbeesthoek failed to achieve the link margin, necessitating engineering modifications to close the link. The findings underscore the importance of geographical location and rainfall intensity in designing satellite communication systems. By establishing a LEO communication ground system in regions with low rainfall attenuation, the total mission cost can be reduced, and system performance improved. This approach can minimize the need for costly system modifications, ensuring optimal performance. The study's results have significant implications for the design and implementation of satellite communication systems in Africa. The identification of optimal gateway stations and the consideration of rainfall intensity can inform the development of more efficient and cost-effective LEO communication systems. This study evaluates the suitability of 6 African ground stations: Cairo, Praia, Port Louis, Abuja, Longonot, and Hartbeesthoek as potential gateways for low Earth orbit LEO communication satellites, focusing on their performance under varying rain conditions. Utilizing the ITU-R P.618-8 model and GPM satellite rain rate data, the research calculates rain attenuation for each station. The results indicate that Cairo, Praia, and Port Louis are the most suitable terminals for LEO communication systems such as Telesat, with high CNR at 0.001%, 0.01%, and 0.5% unavailability times. Notably, Port Louis records high CNR despite higher rain intensity rates. Abuja also performs well when the unavailability time is set to Telesat's recommended 0.5%, making it a potential gateway hub. However, Longonot and Hartbeesthoek stations are less suitable unless used for low data rate transmission in C-band, 6 GHz center frequency. The study emphasizes the importance of considering other system losses such as polarizing, mismatch, depointing, scintillation, cloud, and gaseous attenuation in future analyses. It also suggests that using point rain gauge measurements for each candidate ground station may yield more accurate attenuation results. The research highlights the need for a comprehensive analysis of cloud, gaseous, and scintillation attenuation to fully characterize and establish the link margin for these proposed stations in the future. The paper provides a comprehensive review of satellite communications research, with a particular focus on the impact of rain attenuation in tropical regions. It emphasizes the importance of understanding and predicting rain rate distributions to optimize satellite link budgets and ensure reliable communication systems. Citing numerous studies conducted in various geographical locations such as Nigeria, South Korea, and Rwanda, the authors demonstrate the significance of accurate prediction models to mitigate the effects of rain on satellite signals. These studies underscore the need for precise models that can predict rain rate distributions, thereby enhancing the design and operation of satellite communication systems. Moreover, the paper discusses the role of low Earth orbit (LEO) satellite constellations in enhancing broadband satellite communications. LEO satellites offer several advantages over traditional geostationary Earth orbit (GEO) satellites, including lower latency, higher capacity, and better coverage in polar regions. However, they also introduce new challenges related to satellite visibility, handover, and network management. The authors highlight the importance of advanced signal processing techniques and error correction codes to improve the performance of satellite communications in the presence of rain. They also emphasize the need for further research on rain rate prediction models, particularly in tropical regions where rain patterns are complex and highly variable. In conclusion, the paper presents a thorough examination of the challenges posed by rain attenuation in satellite communications and the potential solutions offered by LEO satellite constellations and advanced signal processing techniques. It underscores the importance of continued research into rain rate prediction models and error correction codes to ensure reliable and efficient satellite communications in tropical regions. I apologize, but it seems that there is no content provided for me to refine. Please provide the transcript or research paper you would like me to refine, and I will be happy to assist you in creating a concise, technically accurate summary suitable for voiceover narration.